All right, hello, welcome back. So far, we have been looking at kinematics of particles, and that is trying to describe the motion, just looking how the motion looks like, and in mathematics, can communicate with somebody how the motion looks like. So we developed a lot of tools and methods to properly find the relationship between these kinematic variables. Now that we can properly describe the motion, now it is time to take a step back and study the causes of those motion. In other words, what are the forces that lead to the observed motion? That is, this studying the cause of motion, studying the forces, is a topic of kinetics. Obviously, you need to know very well the kinematics because that's what the motion is. And what we add here is the relationship between the forces and the motion that we observe. So much of classical mechanics is based on the work of Newton, who first formalized these relationships. I'm sure you have already seen most of these in physics classes, but it's a good idea to reiterate these laws of motion. Newton's laws are related to a motion of a particle, and there are three laws in Newton's words. First one is the simple one. Newton's first law says that if there is no net balance, let me write it down. If no net force on a particle, in other words, no force imbalance. If all forces act on a particle balance out, then two things might happen. If particle is moving, it continues to move with the same velocity and in the same direction. Same velocity means same direction, but let's add that explicitly. Or I wanted to make if particle is stationary, it remains stationary. So both of these essentially mean that the state of the particle does not change. In other words, there is no acceleration. If velocity is zero, it remains zero. If it's non-zero, remains at the same constant value. All of these are when there is no force imbalance. That is the first law. The second law is actually, or the first law is a special case of the second law that talks about what happens if there is force imbalance. If net force is not zero, in other words, there is force imbalance, then the particle accelerates. And the relationship let me continue, right? The particle accelerates with an acceleration that is proportional to size of imbalance force. So if you have more imbalance, you will have more acceleration. We can write it net force proportional to, this is a proportional symbol, to acceleration. And we know the constant of proportionality. Well, let me write it the other way around. Let's write it this way to be consistent with what we wrote. Acceleration is proportional to net force, or we know it that the constant of this proportionality is related to the mass or inertia of the particle, or finally the form that we are all familiar with, F net equals mass times acceleration. This is the second law, Newton's second law, relating the acceleration of a particle to the total or net force or imbalance of forces acting on it. And the relationship between these two is mediated by the mass of the particle. Here you can note that if F net is 0, you will end up with 0 acceleration too. And that is the first law of Newton. Finally, the third law is essentially action reaction that we have heard before. Note that there are two particles are involved. Two bodies are involved. Oh. I emphasize this too. It means that the law states that if particle A exerts force on particle B, then particle B exerts force back on A with equal magnitude but opposite direction. So it is, again, I want to emphasize, there are two bodies involved in this law. If this is A, if this is B, they don't have to be in contact in any way. It could be any form of force, including contact force or electromagnetic force or gravity. If B applies force on A, then A applies the same force, same magnitude, but opposite direction. So if you want to write it as an equation, F of B on A, we'll see that these are all vectors, equals F of minus F of A on B. And that is the third law of motion. So with these, we can start to think how the motions of particles are related to forces and how possibly bodies interact with each other. So that is just a quick reminder of what the laws of motion in classical mechanics are. In the next few videos, we expand on these a little, and we'll see how we can use this to solve for forces that are related to known motion of a particle. So I'll see you in the next video.